To show that a series converges conditionally, we have to verify two things. A, that the series converges, and B, that the sum of the absolute values of the terms does not converge. Let's test the first series on our list here for conditional convergence. First we check A, does the series itself converge? We can use the alternating series test here to show that this alternating series converges. The limit as n goes to infinity of the absolute value of the terms goes to 0, and the absolute values of the terms are decreasing as n increases. Now to check B, we look at the sum of the absolute values and we check if that converges. And the answer here is no, because this is a p-series with p equal to 1/2, which is less than 1. So therefore the sum of the absolute values diverges. And therefore both A and B hold, and our series is conditionally convergent. We found the one that's conditionally convergent, which is what we set out to do, but we're going to check the others for practice. So we said to show that a series converges conditionally, we need to show two things. A, that the series itself converges, and B, that the sum of the absolute values diverges. Now, to show something is not conditionally convergent, we need only show that either A or B fails. If one of these fails, then the series cannot be conditionally convergent. For this series, my intuition is telling me that the limit as n goes to infinity of e to the n over the square root of n is not equal to 0. So I'm going to start with trying to show that A fails, namely that the series itself diverges, and I'm going to use the divergence test to do this. If we cast our mind back to the lecture on sequences, we'll recall that the limit as n goes to infinity of this alternating sequence of the terms of this series is equal to 0 only if the limit as n goes to infinity of the positive part is 0. And now we can calculate the limit as n goes to infinity of the positive part, e to the n over the square root of n, using L'Hopital's rule. And we see, once we've differentiated appropriately and calculated the limit, that we get that this limit equals infinity. In particular, this limit is not equal to 0, and therefore the limit of the terms of this series is not equal to 0. And now by the divergence test, this series must diverge because the limit of the terms of the series is not equal to 0. Now, since the series itself is not convergent, A fails and the series is not conditionally convergent. Now, the same approach applies to the third series on our list. Remember, to show that it's conditionally convergent, we must show that it's both convergent and the sum of the absolute values is not convergent. And again, we see here that the terms of this series are not approaching any limit because they're oscillating back and forth between plus and minus 1. So once again, we're going to try to show that A fails. So we try to calculate the limit as n goes to infinity of minus 1 to the n minus 1, and we see that this limit doesn't exist because the positive part of these terms, its limit is 1, and therefore this alternating sequence of terms keeps flipping back and forth between plus and minus 1. So therefore, by the divergence test, this series also diverges, and therefore it cannot be conditionally convergent. Now for the fourth series on the list, I can see that the sum of the absolute values is a p-series which converges. So I can see almost immediately that b is going to be violated here. The sum of the absolute values of the terms will actually converge. So writing down the details, I see that the sum of the absolute values here is the sum from 1 to infinity of 1 over n squared, which converges because it's a p-series with p equals 2, and therefore condition b does not hold. So the original series, the sum of minus 1 to the n minus 1 over n squared, is not conditionally convergent. It is actually convergent because it's absolutely convergent, but it's not conditionally convergent. The last series on our list is similar to number 4 in that the sum of the absolute values is a p-series with p greater than 1. So we see that it's absolutely convergent, so it makes sense to start by trying to show that b fails. That is, we're going to show that the sum of the absolute values converges. And writing down the details, the sum of the absolute values is equal to the sum of 1 over n to the 3 over 2. And this is a p-series with p equals 3 over 2, which is greater than 1, so we know it converges, and therefore this series converges absolutely. So the series itself converges, but because it converges absolutely, it doesn't converge conditionally. That is, because b fails, it doesn't converge conditionally.